You know, when you picture a volcano, you're thinking fire, heat, molten lava, right? I mean, they are unbelievably hot. But what if I told you that the biggest, baddest eruptions can actually make the whole planet colder? Yeah, colder. It's this incredible paradox, and we're going to get right into it. I know, it sounds totally backwards, doesn't it? How on earth does something that's literally spewing fire and boiling rock cool things down? Well, that's the big question we're tackling today. And believe it or not, the answer isn't on the ground, it's way, way up there, high above the clouds. See, when a huge volcano blows its top, the lava and the ash you see on TV, that's just part of the story. The real drama, the thing that affects all of us, happens miles above our heads, and its impact can stick around for months, sometimes even for years after the smoke clears. So to figure this all out, we've got to look at what's actually getting shot up into the sky. It's not just smoke and rock. Nope. There's let's call it a secret ingredient that's the key to this whole cooling thing. Think of a volcano like a giant pressure cooker for the planet. And an eruption is when it finally lets off all that steam. You get this huge cloud of ash, tons of dust, and this whole mix of different gases. Now, the ash looks super dramatic, for sure, but it's one of those invisible gases that's the real main character here. And that gas is sulfur dioxide. This is our secret ingredient. When a volcano pumps a massive amount of this stuff way up high, it starts a chain reaction, a chemical reaction that can literally alter the climate for the whole planet. So remember that. It's not about the lava's heat. It's all about the gas's chemistry. Okay, so this sulfur dioxide gas doesn't just, float around. It gets up there and mixes with water, and boom, it turns into these super tiny particles called sulfate aerosols. And the best way to think of these? They're like microscopic mirrors. Millions and millions of them. And because they're so tiny and light, they don't just fall back down. They can hang out up there for a long, long time. All right, so we've got the what, sulfur dioxide, but the where is just as important. I mean, for this whole cooling effect to work, the eruption has to be powerful, like really powerful. It has to be strong enough to blast its plume right through all our weather, through the clouds, and into a very specific part of the atmosphere. And that place is the stratosphere. So the stratosphere is way up above the weather. There's no rain up there to wash these little aerosol particles out. So instead, the jet stream and other high-altitude winds just grab them and whoosh, spread them all around the globe. It's like they create this super thin, invisible blanket that covers the whole planet. And since it's pretty calm up there, they can just hang out for months, sometimes even a couple of years. Okay, so let's recap. We've got this layer of tiny little mirrors floating all around the world, high up in the stratosphere. So, what happens next? Well, pretty much what you'd expect mirrors to do. They create a giant sun shield for the entire Earth. So, here's the play-by-play. The sulfur dioxide goes up, turns into aerosols. The winds spread those aerosols everywhere. Then, this new aerosol layer starts doing its job. It reflects sunlight. It literally bounces the sun's rays back into space before they ever get a chance to hit the ground and warm us up. The end result is simple. Less sunlight gets through, and the planet gets a little bit cooler. And this isn't just a tiny change. You can actually measure it. A really big eruption can drop the whole planet's average temperature by about 1 degree Fahrenheit. Now, I know 1 degree doesn't sound like a lot, right? But when you're talking about the average for the entire globe, that is a huge deal. It's enough to seriously mess with weather patterns all over the world. And hey, this isn't just some science theory. This has actually happened. We've seen it in history. And the consequences were, well, they were dramatic. Let's talk about maybe the most famous example ever, when one single volcano caused a global chill that lasted for years. Back in 1815, this volcano called Mount Tambora in Indonesia just exploded. It was one of the biggest eruptions we've ever recorded. And the next year, 1816, got a nickname, the year without a summer. Seriously, there was snow in June in New England, crops failed all over Europe and North America, leading to massive famines. And even more recently, some of you might remember Mount Pinatubo in 1991. That eruption caused global temperatures to dip for about 2 whole years. Okay, so this raises a pretty obvious question, right? If these volcanoes can cool the planet, why aren't we in a constant ice age? Why doesn't the Earth just get colder and colder every time a big one goes off? It's a great question, and the answer has to do with gravity, and another gas that tells the other side of the story. First up, gravity.
I mean, those little aerosol mirrors are light, but they're not weightless, so eventually they just fall out of the stratosphere. It takes a year or two, but they come down and get washed out by rain. But here's the twist. Volcanoes also pump out a ton of carbon dioxide, CO2. And unlike the aerosols, CO2 is a greenhouse gas that traps heat and stays in the atmosphere for hundreds of years. So you get this wild situation, a powerful but short-term cooling effect from the aerosols, followed by a much smaller but way longer-term warming effect from the CO2.
And that's why the big cool down is only temporary. The whole show, from the eruption to the cooling and back to normal, it usually only lasts about 1 to 3 years. It's a really powerful slap to the climate system, but a quick one. So let's recap the whole thing real quick. A massive volcano blasts sulfur dioxide way up into the stratosphere. That gas turns into a planet-wide sun shield of tiny particles. That sun shield reflects sunlight and cools the Earth for a little while. It's temporary, yeah, but it's just an amazing example of how one event can have two totally opposite impacts on our climate. And that kind of leaves us with a pretty big thought, doesn't it? When you see how one volcano in one spot on the map can change the weather for everybody on Earth, it really shows you how sensitive our planet's climate is. Everything is connected. It's this powerful and honestly kind of humbling reminder of the very delicate balance that keeps our world running.